We learned about last week about operating systems, protocols. We briefly discussed some ideas of in-network processing, how we can analyze the data on the edge, or sometimes you might hear the term edge computing, which refers to analyzing data closer to the source, could be on your gateway, could be on the node itself. And also we mentioned this, most of the devices are typically run on low power devices, and you have limited energy, limited computational power. And the current design of these hardware mainly focuses on technologies which they use more power to communicate data in comparison to computational power. If you compute, let's say, some data, you do some aggregation, probably use less energy compared to if you want to send a large amount of data via over-the-air communication. Obviously, if you do more computation, very complex computation, again, energy consumption of computation will be higher, but in relation to what we are looking at, like amount of, I don't know if you send 10 bytes, or if you're going to process 10 bytes, computational energy consumption is significantly lower. Look at the characteristics of data we are sending. Often the data is continuous. There's like single measurements over time, or it could be something like CCTV or video or audio information, which can be a little larger and more continuous. But the big notion of this data is often continuous. It's not just a single value, single measurement. There are measurements over time and coming from space. Then you have time and space domains in this data. Usually the deployments are in large numbers. You might have a sensor sending small data, but if you're monitoring, let's say, a city, a large farm, a marine area, you might have a large number of deployments. Last week we discussed the density of the deployment, understanding of how far the sensors are from each other, how accurately they can measure the surrounding environment. Obviously the quality will drop as you get further from the main source. All these things are important if you are designing, depending on applications, which accuracy of information and understanding of the context of that information, it becomes important. We discussed the application-centric and node-centric architectures. Some of the application designs are, depending on you write a program, just runs on a specific node and you get information. But often in larger networks, you need coordination between different nodes. And these are changing the way that the program works. Instead of a sensor just sending an information to a source, looks around and starts coordinating the application with the nodes around them. Today we discuss some of these issues, and we look at some of the analytical models can allow you to process and analyze data based on these principles. Before moving on, some of the sensors also could come from other sources. Like imagine if someone is in a traffic jam and it starts tweeting information saying there is a traffic jam, actually you can also treat that information as a sensory data. Then sometimes you will see a combination of data coming from textual sources, from human created sources of information which are based on text, and numerical observation and measurements. But with some means you can process or you can understand, you can consider them as sensory information. One thing you have to be careful with is crowdsourced information that can be easily biased. If you're creating a traffic control information which relies on people's Twitter or adjusts its, let's say, traffic lights based on number of people, say how busy the road is, you can get 10 of your friends just every morning tweet and say A3 is congested and avoid people going there. Then you have to be very careful when you're working with the systems. They can be easily biased. And obviously, if we have large amounts of data, we can convert them to the value in different domains. We can look at areas like pollution, traffic, smarter cities, in healthcare. Later during this module, we'll provide you some real use cases, some applications, how actually the platforms we deploy, how the data we collect can be used in real applications. But today, we'll be we're going to mainly focus on accessing data and analyzing the data. Since most of the IoT data is time and location dependent, accessing this data probably needs some parameters. If you're going to access the data, we have probably two key ways of accessing this data. Either is based on publish or subscribe mechanism, or searching for that data. Imagine searching is similar to you have a large network of resources, you submit a query, you're interested in any temperature data which is above X limit, or you're interested in an areas of the city which they have air quality of based on X metric, and your platform is able to go and find that data. Or in many cases, the mechanisms for accessing data is publish subscribe, especially if you are looking for events. For example, if you have deployed your fire alarms all around campus, then you will have a high-level application which subscribe to any fire alarm. If one of these nodes starts sending a fire, that application will pick up that message and will start taking an action. And we will look at some of the protocols and some of the mechanisms which allow implementing publish-subscribe methods. Have you worked with any pub-sub method? Are you familiar with things like RabbitMQ and message bus? What message bus did you use? Mosquito. Yeah, that's an Apache implementation of IBM MQ. Yeah, there are different implementations of it. Today I'll just take one protocol which is mainly used in IoT. I'll just provide that as an example, but there are many different implementations and variations of it. And my example, I think, is with RabbitMQ. The technology doesn't matter here. It's just the concept of how actually use data. Accessing data can be based on an ID. If you know where your source is, if you know where your sensor is, you'll just ask for that resource. You'll say, I'm looking for, let's say if you have implemented your own fire alarm and you know where it is, what device is, you just send the device ID and retrieve that information. Sometimes can be based on object, give me the temperature from this room. Sometimes you add a range of time to it, a range of location to it, and each of them will add more complexity to your query, and then you need to think of how your higher level network functions will provide the search and access to data. On internet and on the web, we take it for granted. We have like search engines. We can just open, I don't know, a common search engine and search for something, and they retrieve us. Usually they retrieve us the pages, not really the information. Let's say most of the current search engines actually are information locators. You search for University of Surrey and your search engine will return a list of pages which thinks they are related to University of Surrey, is related to you, up to you how to click on those pages and open and read the information. In IoT, that paradigm is a bit different, because when you're searching for the information, you're not necessarily interested in the location of that information, you're interested in the data itself. Tell me if there is someone in this room. I'm not interested in there are 5 sources can tell you this. I actually want to know if there are people in this room or not. Then that may change in the design of the network and higher functions on top of that for searching the information. And obviously you can add quality and other measures if your applications need more metadata related to the search and accessing those information. Sensory data itself, it can be just a single measurement. For example, I can put a sensor and I can say that sensor returns a value, 15 degree, let's say, Celsius. Even if you don't add the unit of measurement, interpreting that could be more complex, because 15 degree in Fahrenheit and Celsius, they have 2 significant different meanings. In fact, you need more metadata to explain what that data is. In most of the IoT data measurements, they need to come with some contextual information. When it was collected, where it was collected, the time range, the accuracy, the precision of the device collected that. All this information will make the data more interpretable by higher-level applications and services used. Let's say if you have a measurement like this, most of the sensors, if you program them, you will collect something like this. You can program your XM1000 to send your temperature data. You can add this unit of measurement. This is the time. And if you know the location of your sensor where it's deployed, you can add the GPS longitude, latitude information. This week, we mainly focus on processing and interpreting that data, looking at if I had those data and I had the parameters, how I can actually use them, what purposes I can use them. Especially on their own, the single measurements don't make much sense. I'm interested in the continuation of these numbers, a series of numbers, how I can actually put this series of numbers together to make sense of them in an application in an algorithmic way. Next week, we look at how actually we can specify the metadata for those information to make it available for searching, for integrating data from different sources with different parameters. Today, the main focus will be on this value. Next week, we will mainly focus on how to specify the other parameters which provide context to that value. Starting for the data processing, the processing of data, as we said, can happen on the source. You can collect the data, you can aggregate, analyze the data on the source itself, can happen on the network services, can happen on a gateway, if you have a gateway here. Or higher level applications can take that data and integrate it in other higher level application services which might have other data sources, or do further processing of that data and create value from it. What type of, and you need obviously discovery and other mechanisms on top. What type of processes we can add to that data? What type of methods can be applied to analyze that data? The very first and simple one are methods for example, taking data and aggregating it. Aggregation, you can think of, if I'm reading temperature data every 5 minutes from this room, instead of sending every 5 minutes, I'm interested in the average temperature. To see if the average temperature is below 21 or higher than 21, I might decide to change the air conditioning system here. You can add more information, because just having the average, maybe in some applications, is not enough. You might add more information. You send the average with minimum and maximum. Then you are providing more context, because if your data suddenly went up and down, within that period you are sending maximum and sending the average, you might provide more context of how it changed. Let's say if you're taking my blood pressure continuously, or my heart rate, let's say that makes better sense. If you're taking my heart rate, you can send an average of my heart rate per day, but also you're interested in the peaks and minimums of my heart rate that might show some conditions. Then you might send more information with that data. These are very, very simple measures, but often in IoT applications are useful. And you can think of adding other statistical measures like standard deviation. You can add, I don't know, median and other points of data. But most of this processes, or most of the algorithms you apply to specify, say, aggregated values or to analyze the data, rely on two key things. They are relying on the temporal and spatial correlations. Let's say if I have 4 sensors in this room, you can take average between 4 sensors, and then you have average temperature of the room, or you can take the average of these 4 temperatures over the past 3 hours and send the value. Then if you're taking average for the past 4 hours, you are using the time domain to aggregate that data. If you're looking at multiple sensors measuring the same phenomenon and you're trying to aggregate or coordinate between them, you are using the spatial correlation between them, because you won't take a sensor outside this room to add it to give an average temperature. Now, by using those information, by looking at neighboring nodes, you can start finding edge detection. For example, if you're deploying a set of sensors to look for wildfires, if different sensors start sending smoke and light or temperature information, and you coordinate between different sensors, you can find actually what are the age of the event is happening, and you can follow basically how that event evolves and changes. Obviously, in some cases, you might lose part of your infrastructure. Or if your sensors are mobile and keep moving, if you have pervasive devices, you can start using them for tracking an event, looking at how that event evolves, or track a certain phenomenon. Then often these processes are relying on time, space domain, and also coordination between multiple nodes. That changes the way we look at the networks. In conventional networks, let's say, take internet as an example, we refer to sources usually by their IP address. We use a domain name, www.ac.uk, and that translates to an IP domain, goes to a server, and we get the information. In IoT, most of the time, we are not necessarily interested in the source, we are interested in the data. When I'm looking for the temperature from this room, from the air quality on this campus, necessarily I'm not interested in the device provides that. That changes the way, instead of saying www.sorry.ac.uk/air quality, which you're referring to a specific source, you are looking for the data instead of the source itself. Then that changes the way the networks are designed. Mostly we are looking at data-centric networking and looking at data. Having said that, the parameters of that data in terms of the device's accuracy, location of that device, and everything else provides more context to that information. So I said the aggregation is one of the most obvious ways of analyzing data, especially in the source. If you're doing like edge computing or source analysis, will allow us to make smaller footprints of data. If you have large amount of data, instead of communicating continuous data, you can aggregate it and send smaller data. And obviously by sending a smaller amount of information, you're saving in your energy, in your power, especially in power constrained environments for the sensors which they have a battery life. Very simple scenario. If let's say we had here 6 sensors, if each of them they send a measurement, and this is a multi-hop communication. You have one message from this, one message from this. Now you have 2 measurements here. This measures its own data. You have 3 measurements. And you see by the time they get to the source, you have sent, let's say, 6 measurements. Imagine each measurement requires 4 bytes to communicate. You have sent 6 times 4, 24 bytes. And then if they are using like, I don't know, X amount of your battery power, you basically, you have multiplied that battery consumption by 6. Here, there's a very simple aggregation scenario. Imagine these sensors are deployed in a farm, and you're looking for humidity of the soil, you're just looking for an average. They just send the information and aggregate it in the source, and just one data goes out. Obviously, you have lost some quality. Here you had more granular information. You had from 6 points, different areas in your farm, you had that data. Here you will have an average, but obviously then you might create a network which lives longer on a battery and sends less information. Then you can have more lifetime for your network and collecting information. In different applications, different scenarios, you might choose different ways of looking and analyzing data or aggregating data. But there are few characteristics which are very important on that decision making. One is the accuracy. If you're aggregating data, very simple one, you take the average, you're losing basically some accuracy. The difference between the resulting value and representation of the original data. You need to think of what is the level of accuracy. Even when you're taking averages, you can take average of 10, you can take average of 100 measurements, you can take average of, 10,000 measurements, send a value. That can be 10,000 measurements per day, you send one value per day, or you can send 100 measurements which are averages per hour. That's a decision, depends on the application and depends on the accuracy. How complete is that? If you're sending average, for example, how much you can actually use that to reconstruct the original data? Probably with average, not much. If you send average and minimum, maximum, probably you can construct at least the way that data look like, the signal, a little better. If you use like methods like LZH, that's the normal zip function, like you send, let's say if you had 5 tens, you just say 5, 10, means 5 times 10. With that, actually, you don't lose any information. You might compress what you are sending, but you can reconstruct the entire data back to the original one. The completeness could be 100%, but obviously the gain you get in average in the data, which you were sending only one measurement, is not, again, is much higher than sending like an LZH compression data, compressed data. Latency. Any process you do will take some time. And if you use a very complex process to aggregate your data, if running that function takes like, I don't know, on your nodes, especially with low computational power, it takes 5 minutes to run that algorithm to get that data, to aggregate it, to analyze it, that latency has an impact in that application's accessing data. Let's say, take an average running on your XM1000 probably will take a fraction of a second. That shouldn't be a problem in terms of latency for most of the applications. But if you're running a fast Fourier transform, I haven't tried to see if you can run a fast Fourier transform on your nodes, but probably you can. That could take much longer. And let's say if it takes 2-3 seconds to run that, that will add a latency to generate every time you're collecting data, to generate the footprint of aggregated data. And you need to consider that. Then the footprint of complexity is very important. And overhead. Overhead in terms of the amount of data you generate, and overhead in terms of the computational overhead you generate. Let's say if you're again creating something which is very complex, you've noticed, like let's say in contiguous operating system, you can't have really parallel processing. Then if you're running a complex process, say take FFT, you're also massively using the resources you have. And if continuously you want to send and receive information and do that analysis, you need to look at that overhead. Overhead in terms of communication and overhead in terms of processing capabilities you have. But often if you do aggregation, you're interested to do it closer to the source because that makes more sense. But could be scenarios maybe actually you do that aggregation in cloud networks as well, especially if you want to create more like patterns or abstractions from your data, which I'll give you some examples. Before actually getting to the data itself and accessing the data, searching for ad hoc data, imagine if you know the source or if you know the ID and you have a search query mechanism, that's more straightforward. But looking at publish-subscribe mechanisms, there are different protocols. Usually you have something like a software bus, or it's called message bus, depending on what application or what documentation they are using. And you have a series of publishers. Let's say a sensor can publish temperature data, another sensor can publish humidity data, or instead of data, they might publish alerts, events. You might, let's say, fire alerts. They might send, I don't know, security alerts. And you have a set of subscribers, which are, they subscribe to that alert. Let's say most of the social media applications will use one way or the other of this publish-subscribe mechanisms. You have a group of friends. Basically, whenever your friends publish something, you get a notification on your mobile phone. The software mechanism behind it, you have subscribed to any alert coming from that particular person, and you get that alert. They will use some sort of protocol which will support this type of information brokering. The same concept here. Now, if you're creating a large network of sensors, they're monitoring for, let's say, fire risks, and they're going to generate an alert to say there is fire. If you have 100 of them around this campus, and if you're going to write an application, in principle you have two ways of doing it. Either you're going to do a pooling, continuously go every 5 minutes, every 10 seconds, or whatever it is, go and ask them, have you seen a fire? Is there any fire? And check them and go around. Or you will create something like this. You will create a message bus, which if there was a fire, if there was an alert, they will publish their message there, and you will subscribe to that message. Those sensors might also measure other things, and other people might subscribe to just to read their temperature data, to read other values. And basically we'll work with a mechanism to provide that. There are different ways of implementation. We just heard it was Mosquito, IBM. What is the IBM? IBM MQ. I use just RabbitMQ, which is, again, is another example of implementation for that. Many of these, they will use different protocols for implementing that. RabbitMQ uses AMQP. I don't know what IBM and Mosquito they use. I don't know. But RabbitMQ also has a plugin. You can install MQTT. MQTT, again, is another protocol for publish, subscribe. Again, these are just protocol, but in principle, they will have a producer, which a user application that sends the messages. That could be a sensor, that could be another application. In software systems also is used a lot. You will have a buffer. Basically, you will have a producer which will send information. You will have a software system, and then you will have queues. That data actually can be stored in different queues. And a consumer will basically use this information from this queue. And this is your consumer, this is your producer, this is your software system, this is your queue. Let's call it Q1, and this is your second. And different implementation, different mechanisms will give you different functions. For example, you can create a queue which the values can be stored, and as soon as the consumer reads those values, the queue disappears. You can just basically delete that queue. Some queues will retain the information. They can have different ways of how much information you want to keep, how long you want to keep them, how much you want to retain them. They will have some parameters and some mechanisms for implementation. but very much also depends on the underlying protocol, how much overhead that creates, and how you're going to send this information. One of the common ones used or introduced for IoT is MQTT. MQTT designed to be lightweight, and that's why people think that that's more suitable for Internet of Things application, because that overhead of its header has just 2 bytes overhead. It means if you want to send an MQTT packet to say, I have detected fire, put this in the message bus, say I have detected fire, to say that information, obviously you need to send some header to your software application to say what it is, like this is your header. In most of the cases, that header could be a large, basically have a payload. Last week we looked at IP version 6, for example, payload, what was this? 64 bytes, I think, was something like this, of just to send a packet of IP version 6. It's just a header, you don't know how it started with sending data. Here, MQTT is designed to have 2 bytes, but basically has 2 bytes of mandatory. There are optional headers also you can send, but say the minimum you need to send an MQTT packet will be 2 bytes of header, and then you can send your datagram. Here will be your data. And that header will have some information telling this is, to start with, this is an MQTT packet, and some quality of service parameters you will send with this. Obviously, that's the application level protocol, application layer protocol. Then you need to send it over TCP/IP or any carrier network or whatever you have. You need to be able to communicate it to a destination, wherever your message bus is. But the application layer protocol itself does have a smaller footprint in terms of the overhead. What that 2 bytes actually provide for you, apart from saying this is an MQTT basically packet, you can use that 2 bytes to specify some quality of service measures. For example, you can say, at most send this information once. A few times I have asked this in exam, what does quality measures mean in the context of MQTT? For example, if you're sending, saying at most once or at least once, what is the difference between these two? When you're sending at least once, you want to make sure this arrives at least once, but duplicates also may occur. And guess what? If you run it on CoAP, remember in CoAP we drop TCP in favor of UDP to reduce the information. Then CoAP doesn't have its own quality control. You might use a combination of these to add to your quality control. If you're sending, say, MQTT messages over CoAP, you might use this to add some quality of service measures. But if you do that, then you need to know if you're setting it to at least once, actually you might send the measurement twice. You might send the value twice if the value got lost somewhere or your network basically mixed it up. And that, if that's a measurement, or if I don't know, is saying is fire, you might actually detect that fire message twice. Or if you say at most once, you want to make sure it will deliver, but only will be delivered once. And all you might say exactly once, send it. To do that, MQTT has 2 bytes for quality of service level. Basically, combination of 0 and 1s. You can have 4 combination, and you had 3 of them. I don't know what 00 means then, but you can look it up. Basically, you have 4 combination. I just showed the 3 of the combinations. That's for here, and what came from the previous slide, what quality of service measures you can use. These are the 2 bytes you have. Has a flag here, which is just, when I say flag is 1 byte, could be 0 or 1. Depending on whether you make it 0 and 1, you can say this is a duplicate delivery or it's not. Like again, if you send the data once and you're sending it again, you can make it 1 and say this is the duplicate delivery. And then combination of these and quality of service measures will allow MQTT to decide how to store it in the message bus. There's an interesting flag here, retain. If this is used, if you're putting a message in your message bus, and imagine someone is subscribed to that, and that message is delivered. Usually that's removed from the message bus, which is removed. The message was delivered. If you enable retain, you are telling your message bus to retain to that information. The reason is if there is a new subscriber comes in, then that can access to the last good known value, last value of the message delivered. That's for new subscribers, not for the same subscriber, because you have given the information. Then by changing these parameters in the MQTT header, you can give different indications of how that protocol should treat your data and how the message should be written. But when it comes to the implementation, still you will need something like RabbitMQ or Mosquito or IBM MQ. I don't know which of them implements MQTT, but for certainly I know RabbitMQ has a plugin for MQTT, or there are different implementations of it. This is only the protocol, and then you need an implementation of actually providing other mechanisms to use that protocol. Just be familiar, in IoT, if you are using publish subscribe, MQTT is one of the common protocols, is not the only one, and to use that protocol, you need an implementation of it. Now, once we have the data, once we can communicate, we can put it in a message box, we can provide from the producers to the consumers. Now we are looking at what type of data we are talking about. Especially most of the data will come as continuous values. You read a temperature measurement, imagine your frequency every 1 second. Every 1 second you will read a value. And if you put this value together continuously, imagine each of these are coming in 1 second, basically this will give you something like a signal. You can also look at it as a digital signal, basically, representation. Or in other words, sometimes people refer it as time series data, because this data continues to over time as it has a time domain. Time series analysis, time series data analysis has been around for a long, long time. Looking at stock market is also a type of time series data. If you look at stock market, how they change every second or whatever, someone's stock value goes up and down over time, that's time series data. This is a similar method. Then there are lots of methods actually coming from financial sector applied to time series data. Some of them might be actually applicable also in terms of IoT data, depending on what application you want to use. But you can think of clustering data. You look at the how the data changes, you group the data, and you create similar groups. The days which the air quality has been bad, air quality has been average, and we have perfect air quality data. Imagine if you're measuring your air quality on campus every 5 minutes, you can create methods which can allow you to classify not single measurements, a group of measurements over, let's say, a period of an hour. And that's what we're going to look into in the next 45 minutes. Or you can use this for data for classification, create a group of different data. This is traffic jam, this is slow-moving traffic, based on giving machines some examples. Or you can create more predictive models, looking at regressions, looking at, I don't know, temperature and noise level in this room, and predict how it's going to look like in the next hour by looking at data over the past 3 months, how this room has been utilized. In general, this would be a combination of some analytical models, some simple models to look at these continuous observations, to be able to create more abstractions, more patterns of this data, and some mechanisms of data analytics or machine learning. Especially if you do clustering, classification, if you do regression, you will need some machine learning mechanisms. Within this lecture, within this module, we are not going to talk much about the machine learning aspect of it. We are interested in how actually you can create those patterns, how you can actually group that data to feed that to machine learning algorithms. But in general, machines will learn in 2 ways. Either they will learn by experience. You give them lots of data and they will look at that data and will be able to, let's say, group them, find similarities between them. That will be your unsupervised machine learning clustering algorithms. Or machines learn by example. You will give thousands of examples of traffic data, traffic patterns, say this is a slow-moving traffic, this is accident, this is X, Y. And next time when a machine sees a new data, goes and tries to find the similarity between what you have given in the past, the examples and labels you have given, and what it has, and will say this seems to be an accident in this room. Then either by experience you learn or by examples. Very much similar to human learning, basically. It's an imitation of human learning, but much, much simpler and much, much limited. In terms of time series data, going back to our data, one of the very first things we do to analyze time series data is doing segmentation. What we do, we have continuous measurements. On their own, they are, well, sort of simple and at the same time complex because we cannot really interpret them what they are. But we want to put them in groups and look at, within a period of time, within a group, how they have changed. And usually that abstraction gives us a view of changes or patterns in that data. Basically, we want to move from single measurements to patterns, abstractions, whatever you like to call them, to aggregated values. To do that, we need to be able to first to decide how we're going to group our data. The terminology I've used here, I'm using segmentations. You basically divide your data into different segments. Imagine if this was a measurement, take it as a temperature, well, noise measurement, take it because it's more similar to something changes rapidly. Each of them are measurements. Imagine if this is time, my sample's probably coming like every 5 seconds or whatever it looks like. And if you put all this data together, you will have a signal like this. Now, to analyze the segments, I've decided to take every 75 measures to put them in a group. And each group will be a segment of that data. This is my segment 1, segment 2, segment 3. The next is how to create a representative of this segment. The very first and simple one you can think of, what would be to do? What can you do if you want to represent this segment? To take an average. Yeah, that's the most simple one. Instead of sending the entire data, I will send, I don't know, here it will be probably something like 0.5, here will be 0.55, and here will be probably 0.6. This is pointed. I'll send 3 data. But that's not a really good representative because this data has gone a lot up and down and I'm missing all that information. What else can you add to that to improve it? You add minimums and maximums. Here you say probably your minimum is close to here and your maximum was here. Here probably is your minimum and that's your maximum. That will give us a little better context of that data. You can add a standard deviation to say how much actually variation you had. Probably in this one, it seems like we have more variation compared to the other two. And if you add that, then you can say how much change happened within that period of time. But these are still very, very primitive. They don't really give us a good indication. And obviously, if you want to send everything, imagine every time you want to feed it to a machine learning algorithm, to analytical algorithm, if there are 75 values, you have a vector of 75 values. It's difficult to process. It's really difficult sometimes to make sense of it. If you can create an abstraction of it, which shows sort of a shape of that signal, shape of that change over time, and also was smaller, that would be a brilliant way of presenting it. But how can we do that? There are different methods of using this. You can think of, you can actually take a Fourier transform. If you do a discrete Fourier transform, you can actually separate them to different frequencies. You can do a wavelet transform. Are you familiar? If you do computer science, probably not. If you do electronic engineering, probably you know. And if you don't know, it's okay. I mean, it's just I mentioned it for the sake of completeness. Have you studied in computer science Fourier transforms or wavelet transforms? I'll be surprised if you do, yeah. But forget about this. But you can, let's say, do complex mathematical functions to separate data. Well, we are not going to go into that. We are looking at something much simpler, and we are looking for something to give us a better representation of that data. That's one of the reasons I actually didn't add any information to FFT and wavelet. I just mentioned it if anyone had an interest. One of the very interesting and common methods of actually taking from this data and being able to create some sort of a pattern representation is a method called symbolic aggregation approximation, SAAX. Again, this is not the only method. I just picked it up because I thought it's simple, and with the background you have, doesn't need much mathematical background to understand how it works, and actually is a very effective method. And also I thought, actually you can implement it on your X1000 because the computational complexity is not very high. And also the implementers had given the code. I've added a part of a MATLAB code. Actually, you can use that MATLAB translated if you want, but it's very simple to write the code. In principle, what SAAX does if you have a data like this, I think this was a real noise data we took from our test bed. If you have a data like this, and if you divide it to different segments, it allows you to represent that data using symbolic representation. Basically, you move from numerical representations to alphabets. You represent it as symbols. Your continuous measurements, like this is 100 measurements, that 100 measurement is represented as 3 strings. And by string similarity, from left to right, take your string, the more similar they are, your patterns are more similar. And now you can think of looking at similar patterns, putting the similar patterns in a group, training an algorithm saying this pattern meant an accident, and next time if it sees a similar, the algorithm sees a similar string, will say, oh, that looks very much like the previous example I had seen, or previous 100 examples I had seen. Then once you start moving from that numbers and single numbers coming over time to something like string representation, you can start thinking of really interesting applications. But how does it work? How actually SACS takes numerical measurements and generates a string? Just some background to it, was developed by Jessica Lin and her colleagues, and I think supervised by Emon Keogh at University of California in Riverside. It extends an algorithm called PAA, piecewise aggregation approximation, and does some mathematical calculation to create those patterns. PAA, it's scientists, they like to use complex words. It's just basically average. When I say PAA applied to a segment of data, means all the values taken that piecewise aggregate approximation, means piecewise you have taken it and aggregated means you have taken the average of that. But yeah, it's a bit of fancy for that. SACS transforms a time series of x length, as length n, to something smaller. Usually, and you have a set of alphabets for doing that. And alphabet size is got to be bigger than 2. Means bigger than 2 means 3, the minimum length. And you will see why. In a minute, you will notice why actually uses more than 2 alphabets. And these are symbols. When I say alphabet, it doesn't need to be English A and B. If you have 3 symbols, you might say my patterns will look like this. It doesn't matter what you're defining it. It's just there are symbols. You can define anything, but you'll use like an English alphabet, but you don't have necessarily to use them. Or you might say my patterns are A, B, C, D, E, F, G. You don't have to have exactly the same sequence of symbols. Basically, it's a symbolic representation. What you choose, it will. You need to just be aware of that, and you will use the same concept which you've used for comparing it, for interpreting them. But in principle, they are just symbols. For here, most of the examples you will see, I will use ABC. But in principle, be aware you can use any other combination as well. How does it work? First, we take the data. We take our continuous measurements, which are going like this. We divide them some equally sized segments. We call them equally sized frames. Each of them will become a frame. Then I have my frame 1 here, frame 2, and frame 3. Once you have your data frames, you will take a PAA of that. That will basically, you will take an average of this. PAA. Here, you will apply your PAA here and PAA here. And obviously, your segment is much bigger. Let's say if my segment was 100, within that 100 segment, I will have, let's say, frames of 10. And each 10 of them, I will take an average. Then if my first segment had 100 values, I will have 10 frames, and each frame will have just 1 value. Then if I go back to here, imagine this will become your segment. Within this segment, you will have, let me change the color. You will have, let's say, I'm just using, let's say 4 frames. And each frame will have whatever the value number is. And I have, for each of them, I will take the average. I will have, let's say, average 1 here, average, let's like PAA. It's better. We'll take the average. then for each segment, let's say here, I will have 4 values instead of 1. Here, like, let's say if it was 75 values or whatever it was, instead of that, I will have 4 values for that. First, I divide it to some equally parts, and then you slice your data twice. You slice your data to segments. Within that segments, you create some frames, and then within those frames, you start aggregating. Once you have aggregated your data, let's say if I had 100 samples, and I divided them to 10 equally areas of frames, for each 10 value now I created an average, I will have now 10 values. First I went from 100 values to 10. I've already saved 90 values. Basically, representing my data now with, say, 10 values instead of 100. Is that clear? Obviously, that choice of how many you take in one frame and aggregate it will have an implication in the accuracy of your algorithm. The more data you aggregate, you average, the more detail you're going to lose, right? The less you take, you will generate more data. Then what you use as PAA will have an implication in the accuracy of your SAGS patterns and the reproducibility of the original signal from what you're taking from your SAGS data. I think that was the exam question last year. What would be the implication of changing the frame size and changing the alphabet size and string size? I haven't talked about alphabet and string size, but generally already you can see the frame size you're creating will have an implication in the accuracy of how representative that data becomes. Once you did it, then you first start dividing your data in frames, and then you start normalizing the input data. Before taking the PAA, you first normalize data. My apologies, I forgot to mention that. And one of the reasons you normalize data in SAGS, you don't want to create patterns from different, say, variation of data. For example, if temperature here varies between -5 and 25, and somewhere else varies between 20 and 22, you want to create an equal way of actually comparing them and look at their variations. Then to do that, you normalize your data. Are you familiar with the concept of normalization? If I give you a series of data, I ask you to do Z normalization. Okay, I'll mention briefly how you normalize data. To do normalized data, we use a standard normal distribution model. That's basically a distribution model of mean of 0 and standard deviation of 1. Before I go any further, do you know what is standard deviation? Do I need to explain it? Our CS students? No? Okay. I'll explain what standard deviation is and how you calculate it. First, let's start saying we are using a Gaussian distribution. We are basically trying to fit our data to normalize it and put it in a standard Gaussian distribution. Do I need to say what Gaussian distribution is? Quiet means yes or no? I'll explain what Gaussian distribution is as well. Normal Gaussian distribution is based on the central limit theorem. Let's say if you're continuous, read that definition for a minute and I'll say what it is. I don't want to read that text. You just read it and I tell what it is. The idea is, if I monitor something, a natural phenomenon, and if I have large volume of data, that tends to have a normal to measure. If we take temperature in Guildford for over the past 10 years, the average seasonal, this will change over seasons, let's say over spring. The temperature will probably now with global warming won't be very normalized, but you will have an average of some sort of, 15, 20 degree. And then over time, you will have some extremes of very cold and extremes of very hot weather. It's basically anything you take and you collect long data measurements, you will have some normal distributions. Now we have a normal distribution in terms of also probability, like probability distribution. Obviously, if normal distribution, standard normal distribution will have now an average, a mu of, what was it? 0, standard deviation of 1. Did I say correctly? Yes. Which the average, if you normalize everything, if you just scale it in a way, which you're basically putting under a curve, you say, whatever you've done, you want to put the average to become always the average to become, mu becomes 0, and your standard deviation becomes 1. I'll define, if you don't know average, basically, you know, is the mu is just the average, and a standard deviation, I'll show the formula, how you calculate the standard deviation. But imagine if you put it under the standard normal distribution, your data will have a curve like this, which within this curve, your mu is always 0, your average is 0, whatever you measured it, and the standard deviation will be 1. How much you deviate, basically standard deviation, how much your values in average deviate from your mean. That's the very simple definition. I'll provide the mathematical definition in a minute, right? And then we have the concept of now probability distribution. If we are looking at the probability of things happening, we can also look at the probability as a Gaussian distribution. Have you studied probability theory? Do I need to define it? Like, let's say probabilities are in two ways. There are discrete values and there are continuous values. Can you provide me an example of a discrete value?
The number of students in the class.
Number of students in the class, that is a discrete value, yes. Flipping a coin. I'll use the coin example because it's simpler here to show, but your example was the correct. If I flip a coin, I will have head or tail. If I have a graph like this, I will have either head or tail. And what is the probability of having a tail or head? If I have a fair coin, the probability of each of them will be 0.5. Assuming if I have a fair coin. If you don't have a fair coin, you could be 20, 80%. But this is the probability distribution. My probability distribution in a discrete value, it moves between tail and head, and each of them will have 0.5. And the area of this together, the probability will be 1 if you add both head and tail. But what if I was measuring the likelihood of having, say, an X millimeter of rain or November in Guildford? What would the value? If we say that value is not exactly a fixed one, I would say, well, I would say 100. You might say, no, it could be 100, 001. Someone said, no, it could be actually 100, 100, 01. Some of this could be 120 millimeter, right? You can add values. Then having the actually probability of the exact value is probably close to 0. Because this is a continuous measurement, it doesn't have a single, it's not number of students, it's not flip of the coin, it's a continuous value. That rain, depending how accurately you measure, you can have really different numbers. And probability of having exactly this amount of rain, probably you have to wait for 100 million years, or probably will never happen. And that is close to 0 in a probability theory. 1 divided by 100 million probably is close to 0. Then we represent that with a probability distribution function. Let's say, if this was the value of having 0 rain, probably is not very likely. Here it probably will rain in November. And the chance of not raining much, if this is 0, probably let's say here is 10. I don't know what would be the average here. 100, let's say 120 and 300. Let's put it this way. The chance of having no rain probably is close to 0. Probably an average rains here is around 100. And the chance of going actually higher probably is 0. And going more than that probably is 0. Again, obviously the assumption is this is a probability density function. If you take a single value, if you take exactly a value here, that probability is 0 happening. But usually we are looking for the likelihood within the range. What is the likelihood between having 10 to 11 millimeters of rain? And the area under this curve will give us the probability. That wasn't really area under the curve. Area under the curve, really under the curve. Will give us the probability of that actually happening. It's a likelihood function. Why it moved? Now, the entire SACS mechanism works based on this concept. Do I need to explain it again? Because if you learn this, the rest of Sachs' method is just a piece of cake to understand how it works. Do I need to explain the probability density function? And imagine if anything we are measuring, the Sachs designers have made two assumptions. First, you're going to normalize it. You're going to normalize it. When you normalize it, you're going to create a Gaussian distribution of it, and you're creating a standard Gaussian distribution, standard normal distribution of that data. That's the first assumption they have made. And also they are making an assumption, if you monitor any phenomenon over a long period of time, you will have a Gaussian distribution of that. Or you can make an assumption that that could have a Gaussian distribution. If you do that, then the probability of the values you're going to create will be something like a Gaussian distribution. You will have something like this. Let's say if you are measuring the temperature here, the assumption is the value of temperature here, what will be the temperature around here? Would be around 21. Let's say the chances of the temperature here goes, let's say here is 21, this room. And here is a temperature of -5, and here is 50. Probably we are starting with a 0. Most of the time this room could get cold a little at night and maybe a bit unlikely to be hotter than that and will be 0. It could be a Gaussian distribution. Then if you are putting a sensor measuring this data, assumption is if you normalize it, will we have a Gaussian distribution? If you normalize it, we'll have a mean of, if you normalize it, we'll have a mean of 1 and a standard deviation of 1. Basically, you're also scaling it down, normalize it. Yeah? Once you've done it, first look at how we do it. To create that normalized representations, we need to take each value, basically subtracted by the mean divided by standard deviation. That's how you do Z normalization. That's how you create your normalized values. If I have values of 1, 2, 3, 4, you take the mean, you find the standard deviation, and then you divide the minus each value minus mean divided by standard deviation. And that will give you the normalized value. How do you calculate the standard deviation? You take each value, you minus it by mean, square it, and then add them up and take the square root. Basically, each value of CI minus your mean, power 2, you take it sigma I from n and take a square root. That will give you your standard deviation. It will give you a measure to say how much people in general deviate. I used to do it, I think I still do. For my exam, we do it for our exam marks. When we take your exam marks, we find what is the average. Let's say the average for this module comes out for 62, and we want to see what is the standard deviation. If it's high, like standard deviation is very high, means we had people who really, really scored low and people who scored massively higher than that. That means we didn't have a really good distribution of data. But if you take your average and you have, say, a reasonable standard deviation, let's say in this case 10, means you're in average, your marks will be between 52 and 72, which seems normal. And imagine if we have a large number class, let's say if you have 100 people, that's what you expect to see. Then again, you need to sufficiently large number of measurements. If you take 3 students, that can be completely biased, because if it depends on how the students, that 3 perform. But if you have a large class, probably you need to expect to see some sort of normal distribution in that data, right? Now our measurements. These are our sensory measurements. First, calculate your standard deviation and your mean. I did it the other day in Python, and that's probably what it will take in a high-level language to do that. Where is it? Make it bigger. Probably in your X1000, I don't know how to make it larger, probably. In your X1000 will be a little more complex than that. Well, in a high-level language, will take something like a 3 line of code. You can write something like that. The reason I showed that, I wanted to say how simple it is to implement an algorithm like Sachs. especially in higher level languages, what happened. In your X1000 with your C, you need a little more effort, but shouldn't be that difficult to do. Sorry, this is a slow in compiling my PowerPoint. Once you have created that, once we have our normalized distribution, again, we did a Z normalization, we used mu and sigma standard deviation and mean, and we took each value minus by mean divided by standard deviation, and we created normalized distribution. This is the normalized data. Now, no matter what magnitude of your data has or how it changes, when you do normalize it, you're creating a series of measurements, which if you take the average, if you take this data, now average it, the average should be 0. Average of that data, the mean of that data should be 0, and the standard deviation of it should be 1. Basically, we are creating a normalized distribution of that. And again, going back how I calculated first the standard deviation using this formula, and average is just take the numbers, divided them by the number of them, and use those to create Z normalized. In the past, in the exam, usually if I ask for something like this, I don't give you something which is really complex for calculation, but I have a calculator, and often actually I do the calculation for you, and also I give the formulas. I don't expect you to remember, even the basic formulas like standard deviation. If required, I'll give you the formulas. But the only thing probably I won't give you that would be the formula to calculate the mean. Right? But the rest should be given. I think 1 year actually, I give exactly this series of numbers and ask a question. Probably I uploaded that question on SariLearn. Actually, I took exactly these values and asked a question about it. But let's say we took our original measurements. These are my sensory measurements. Imagine these were temperature sensors. We created Z distribution of that data. Once we have the normalized distribution of that data, the next step is doing the PAA. And PAA now I've created frame size of, when I say W means I need 5 frames. It doesn't mean the frame size is 5. It means I'm expecting to have 5 frames. What happened? How do I go back? Sorry. Means I'm looking for 5 frames. If I'm looking for 5 frames in this data here, means I have 10 values divided by 5. We will have each of 2 will become 1 value. This 2, this 2, these 2. There's a negative here. Sorry, it should have been here. Negative, this 2, and this 2. And you need to calculate the PAA. What will you do to get the PAA? You basically add them up and divide it by 2. And that was my exam question. But it sounds very complex when I ask in the exam. I gave all the Z original data, I gave the Z normalized data, and I gave the W, and I said, calculate and show me the PAA representation of that data. And many people found that that's a very complex question. But in simple form, if you would have studied it with just taking those numbers, dividing it by 5 equally segments, and take each 2 and average, then that would have been the PAA representation of that data. Once you have the PAA, now first we lost some of that now detail, because we have taken here, like every 2 measurements here became 1 value, but let's say out of 10, now we have 5 values. The next step in stacks is to take these values and represent them by symbols. What would be the step to take from here to the symbol, to a symbolic representation? That's the very interesting, I find it very interesting and clever part of stacks. How it does that. Sachs assumes, because you normalize your data, and because you have a normalized distribution, you have a probability distribution which is normal, is a Gaussian distribution of the probability, says if you took your data and your data follows a probability distribution of normal, I take the normal distribution, I divide it to what in Sachs they call it equally probable areas. Means the areas which you have equal probability of things happening. Means once you are closer to the peak of this distribution, you will have narrower areas because the probability is higher. If you're going towards the tail, you will have bigger areas because The area under the curve is our probability, right? If we are closer to the top, area under curve will be higher because the altitude is higher. We are moving to the corners, area will be bigger, but the surface is smaller because we are smaller in terms of amplitude. In terms of the representation of the probability. Sachs says if your data keeps happening in a Gaussian way, and if you have normalized it, let's divide that distribution to areas of equiprobable area. And depending on that value, assigned an alphabet to each area. Before I talk about this table, let's look at this. If this was my probability distribution, which once you have normalized it and once you have large sufficient data, your probability distribution will look something like this. Sachs says, depending on how many alphabets you have, divide that area to the number of alphabets. If I'm using 3 alphabets, divide the area under this curve to 3 equal areas, for example, and call it A, B, C, for example, if I have 3 equally probable areas. If you have 4, divide this curve to 4 areas, 5 areas, depending on how many you have. And when I say equiprobable area, means the area under this curve, this part, and this part, and this part, and this part, each of them will have equal probabilities. Means probability of things being smaller than minus 43 is equal to the area of probability of things being higher than 0.43, if you normalize it. Basically, you're assuming if things are happening based on a probability, let's assume what are the equal probability of these things happening. Once we do it, for each area we assign a symbol. Once you do that, you need to do it once. And if again I ask this in exam, I'll give you the table. Because all your probabilities are Gaussian, and all of them are divided to the equal areas under the Gaussian curve, and these cutoff areas are always the same. In your program, you can always hard-code them. You can just add it in a lookup table. Once you have it in a lookup table, then if anything happens within this range, for example, anything, here is difficult, anything smaller than this will be A, anything between this will be B, anything higher than this will be C. Here, anything smaller than this will be here, A, anything between these two will be B, anything between these two will be C, anything higher than D will be D. Then you can increase the number of alphabets. Basically, you take that curve, you slice it to areas which you think the chances of things happening are equal, and you give a number. For example, if the average of temperature here in this room is 21, probably the values will be closer to 21, will be many values. Then I will take a smaller slice for 21 areas because I think there will be, many of them will be 21. The things will be less than 20, which is this part of my curve, probably there will be less values. Then I will give it a longer range. But in overall, number of things which will be less than that value will be equal. The number of the things will be between 21 and 21.5, and the number of things will be more than 30 will be equal. That's the assumption. Did I explain? I still think some of you are not convinced. Looking at your faces, I'm not convinced everyone actually got what I'm trying to say. Do I need to explain it again? You can always say yes. Or you can say no. Do I need to explain it again? No. Okay. I explain it one more time. We are measuring... let me clear this. In Sachs, we are assuming our measurements are large enough and long enough. You're running out of time, but I'll be quick. We are assuming our measurements are long enough and large enough to have a normalized distribution. A normalized distribution means we can actually assume they will have an average, and lots of numbers will happen around that average, and they will have a tails of extreme lows and extreme highs of that value. We represent that as a probability, and to make that probability a standard probability, we normalize it. You saw the formula how we normalize it, and take it from us, that will create a normalized distribution. That normalized distribution will have a Gaussian curve, which always the mean will be 0, and the standard deviation, which I show the mean with mu 0, and a standard deviation of 1. Even that's not very important for the sake of argument we have here. Now, if we have that Gaussian distribution, we say, let's say the measurements were mainly around 21. We measure temperature around 21, average here. Then the lots of values will be around the average, will be between 21 to 20 to 21. Most of the values we are going to read will be between 20 and 22. Mainly will fall between 21. We will have extreme cold spells here, which will be below 20. And we might have some occasions of actually larger than 20. Did I say? Now, we are dividing that number of, this is the likelihood. What is the likelihood of something happen to be bigger than 20 in our measurement? Sorry, 22, this was between 20, yeah, 22. What is the likelihood of things happening to be larger than the range of average? What is the likelihood of things happening much smaller? Probably there are less, but there will be more number of them. Then we are dividing this curve to areas which are equally likely to happen. Let's say here we might have larger range. This could say change between -5 to 20, and we might have, let's say, 100 numbers here if we were measuring 300. If we are taking here is between 20 to 22, probably we are assuming we'll have 100 measurements here, and anything below over 100 we are having, again, we are assuming we'll have 100 measurements. We are looking at equally probable areas of happening. But you see the range here is much higher because area under the curve is smaller. Here it has a larger magnitude, and the area under the curve will be much larger. That's an explanation of how you divide a Gaussian curve to equally probable areas. Sorry if it was tiring. Once you've done it, once you have divided your sacs to equally probable areas, you can divide them to 3 areas, 4 areas, 5 areas. The sacs developers went up to 10 equally probable areas. And each area will be equivalent to an alphabet. Each area you have assign an alphabet. Assign ABC, assign, I don't know, characters in Mandarin, assign characters in Greek. Do what you like. There are symbols. They don't matter as long as you take the same convention when you're interpreting them. Right? Once you have done it, now your values can be assigned to those alphabets. I'll skip that, then I'll show it with our numerical example. We took this data, we normalized it. That was our original measurement. We took and we did the PAA, and that became our PAA representation, basically was average. And we are assuming we have 4 alphabets. Going back to our table, I've written the cutoff measures from here. And these are alphabets I'm assuming, A, B, C. Look at this data and you calculated it. You tell me what it is going to be. The first one will be here, right? Between this. Let's write it here is -670 67. Anything goes here this way will be A. Anything goes between these two will be B. Anything between these two will be C. Anything higher than this will be D. Right? That was an exam question one year. Again, can't be easier than this, can it? I've done all the calculations. Obviously, if someone hasn't studied sacs, no way to answer that. Oh, maybe. Okay, what would be the first one? Will be B. What will be the second measurement? 1.63. 1.63 will be bigger than this value. Will be D. What will be the third one? Minus 0.6. 0.06 actually. B or D? B. The third one? This is 6.1. C. And the last one? Oh, sorry, this has a minus. Sorry, I apologize. This has a minus. That's correct. With minus, what would it be? Well spotted. Will be B. And what will be the last one? That would be a C. Okay. Now we took this 10 measurements. We created a string of BDBB. If your next string came BDBB, you know it's the same pattern. If it came BDBBC, you know it was very similar. The last part of it, that end of the tail changed. If the middle character changed, you'll see. Basically, it's like strings. Forget about they don't make any meaning in the human understandable language, but in terms of strings, string similarity will tell you how similar they are. And obviously, if you want to take it and make it with 3 characters, let's look at the cutoffs. I think the cutoffs are -43, I'll check in a minute, 0 and 0.43. And let's take the alphabets of 3. You tell me 3 alphabets and we use them. M, N, O. Tell me if you use 3 alphabets. I think these are the cutoff points. Sorry, this is 0.33. If you use 3 alphabets, what would be the... And if you are using M, N, and O to represent them, what would it be? The first one? Less than will be, let's say anything here will be M. Sorry, yeah. I think it's 0 -3, but yeah, sorry. Again, good point. We need only 2 values. Anything between them will be N, and anything below them, above them will be O. Okay, what will be the first one? N or M? Will be N. Why M? Is -0.3. No, M is anything smaller than. Is N or M? N.
No.
M.
Yes.
Go and calculate it, it will be N.
Wouldn't it be faster to do PAA than normalize?
Okay. If you do PAA, you don't normalize it.
No, I'm just saying swap the order of the values so there'd be less stuff to normalize.
Oh, you do PAA first and you normalize it.
There's less stuff to normalize.
You need to think carefully if that's going to change anything in your Z normalization. Write it and calculate it. I need to think a little carefully. Most probably not in terms of what will happen if you say do PAA first, your standard deviation and mean will change. And the way you calculate the normalized distributions will be slightly different. That will be the difference, will be different. The results will be different in terms of how, because if you first do the normalization, you are taking the real values and you're taking, we distort in terms of creating the Gaussian distribution. No, it's not a good idea. Do it and you will see why, sorry, you have an, okay. Go and calculate this. It's not just that there are 3 values and take them and use different alphabets and see what it's going to be like. You can use any other alphabets. Probably if I ask something like this in an exam, I might give you a similar example. I give the cutoff points, I give you the alphabet and ask you to go and calculate or ask PAA. Well, have a calculator. Okay. Once you have SACs, you're running out of time. Once you have SACs, now you can look at different patterns, you can look at the pattern similarity, you can see how different things are related. With one exception. Now we took numerical values, we changed them with alphabets. We said they are A, B, C, we could say they are A, L, M, we could say anything. Then if you're taking your string similarity, or you're taking, let's say, Euclidean distance, that won't work here. If these formulas are scary, you just ignore them. I just added if someone is really interested in. But basically it's saying, if you have numerical values, if you want to find the distance, if you had 1, 2, 3, and 1, 2, 5, there were 2 frames, you wanted to find their similarity, what you would have done, you would have taken, this is Q, this is C. Q, I, C, I. You would have taken each of them, you would have minus them and you would have used this formula to find the distance. That's basically finding distance between two vectors in a Euclidean distance, if you're interested. If you had numerical values, you would have done that. If you had PAAs, you would have taken the PAA values to do that, right? It's just the hat sign, it just only shows the bar shows the PAA, they are not the real values. Still, you are in a numerical domain. But when you are changing to alphabetic representation, these formulas won't apply anymore. Your formula will look something like this. Obviously, sorry, I forgot to say, this is if you're doing PAA, you're also applying basically based on, you had n values. That's the total values. And this is the frame size. Because you divided your data to a number of frames, you are just multiplying. If you're using numerical distribution, numerical distribution is one of these formulas. Either the simple one, take each of them, 1 minus 1, this would be 0, 0, 3 minus 5 will be 2. And we are squaring them and then taking square root to eliminate the negative. We are taking the real difference between them. This will be 2, for example. Here the distance will be 2. 2 power 2 square root will be 2. If you're taking PAA, just take the PAA values. But once you change it to symbolic representation, now if you have two patterns of A, B, C, D and A, B, B, C, you cannot just say, what would intuitively you might say, well, I go and take their ASCII code. Most of your string similarity measurements in Java, in Python, whatever you're using, will take their ASCII code and we'll look at the differences between the ASCII code and we'll say how similar they are. But that's correct. ASCII is a convention, right? And who says the sequence of them here makes meaning? Because we can change that. We put the symbols as we like. Then what would be the best way of measuring this too? If this was my Q and this was my C, say, pattern, how do I measure this too? Sachs, the designers, came up with a distance function. They said that distance function here we had needs to be changed to a different distance function. In a simple formula, I'm not going to go to the formula description, but in a simple way, they say if you're in a neighborhood, if you're between two areas, your distance is always 0. If you're dividing your Gaussian curve, I don't know, to 3 areas, if you were here and here, the distance between them will be, means distance between two consecutive ones, A and B, always will be 0. And between B and C will always be 0. Means the distance between A and B and C, they're always assuming is 0. That's this part of it, right? And they are saying if you're far from each other, take their beta cutoff points, because those alphabets came from the cutoff points to start with, just takes the cutoff points and basically minus them, put it here, and the rest is numerical calculation. Basically, that Euclidean distance is changed now with the cutoff points, with the beta points we had. Again, I don't want to record, I don't want you to remember any of these formulas, but at least I'm expecting if I gave you these formulas and I said, use this, and these are the beta points, these are the two strings, can you find the distance between these two strings for us? And probably I won't give you very difficult numbers to calculate, just some simple calculation. You should be able to do that. And if I explain what the parameters are as well. Any questions? And the table will look like, for example, for 4 characters, will look like this. And again, because the beta points are not changing, you can always assume this is a fixed value. You can just calculate it once and you have it forever, more or less. If you're writing your XM1000, you have something like this. This is the MATLAB I took from Jessica Ling's website. It's like a few lines. You can always calculate the distances between your... if you don't know MATLAB, don't worry about it. It's just showing basically the cutoff points and simple calculations, how you can do that. But you can translate it to C. You can write it in different languages. And if you're doing if you're writing this in XM1000, the fun part of it is calculating the square root. Good luck with it. By default, you don't have like math.h, all the math.h libraries. There are ways of doing it. Any questions? Okay, a few quick things. We are running out of time. I don't want to rush, but I'll explain some of the important things. The next point, once you have created patterns, now you can analyze them. You can, as I said, here we are not going to talk about the machine learning, but you see we have prepared our data to be fed to any machine learning algorithm. You can do classification, you can do clustering, you can label data, you can have lots of large volumes of data and create patterns, train methods to learn those patterns. You can label patterns. You can take people's heart rate every 10 minutes, create a pattern of it, and then start putting those patterns into groups, label them, do different things. You can take, I don't know, noise data coming from a machine and create patterns and say whether the machine is working, not working, seems to be like part of it is broken because the noise has changed. You can do lots of things like by monitoring different phenomena and creating patterns of it. Another application of looking at time series data is doing change detection. Like if I have a signal like this, what we are looking for the change points. And the change points here, the data can vary a lot, but some of them are just variation. What we are interested in is suddenly if the data changes direction. If you look at this data, even if it varies a lot, but it's moving like in a sort of a steady way here, suddenly this data takes a sharp decline. And there are algorithms not sensitive to the smaller changes, sensitive in change of the trend of that data. This was a stock market that shows these are slight changes during the day, but suddenly your actually shares are going down or shares going up with some variations. And you're interested in the change detection. Why I use a stock market? Because lots of these change detection algorithms are coming actually from financial markets. You might have single source or you might have multiple source looking at. This is an example of multiple sensors together, and this is a single source. One of the most common algorithms for change detection is an algorithm developed in, that's an interesting one, in 1954 called QSUM, as cumulative sum. Basically what QSUM does, you start here, your windows are not equal size. In SACS, we're dividing data, slicing our data to equally sized areas. Here, your windows, they keep being increased, and every time you have a new value, you calculate mean, and you are calculating your standard deviation. And once your standard deviation and mean they go over a threshold, you're assuming, standard deviation goes over a threshold, you're assuming that's a change point. And then you start your window again. Then you have an expanding window, you go expand it till you find a change point and you start a new window. And then there are different algorithms which can detect a change in one direction, in two directions, depending on whether you're sensitive to both ends of standard deviation increasing, decreasing, or you're just looking at one level of it. Yeah. The most common algorithms are looking at changes in two directions. Basically, and you see the windows are not equally sized. Every time you find a change, you stop here and you start a new window. Again, these are called expanding windows. Basically, you keep expanding it till you find a change point. Every new value you read, you calculate the mean, you calculate the standard deviation, and if suddenly you go higher than standard deviation, you say this is a change point. Another model is just an example, actually learning like to predict a value on a node itself. Let's say if I have a sensor node, sending a value, and that's measuring a phenomenon which doesn't change much, and sends it to a gateway. Let's say temperature of this room doesn't change very often, but I want to know the temperature, and I measure it every 5 minutes. I measure it for a while, and I create a regression model. Do you know what a regression model is? It's basically, a regression model is you give a series of values, and the model learns and can start predict how that value is going to look in future. You measure the temperature for a month here, you learn what the temperature based on time looks like, and then you start predicting like that. One model is used in sensor networks. Some people have these guys came up with an interesting idea. They said, well, I measure something, and I start learning that, and I create a regression model, and I start predicting that data. Then this is your source, and this is your destination. So I create a model, and I share it between the source and destination. Let's say I have a sensor here, measures the temperature, and over time I've created a model which can predict that temperature with some accuracy. And the more accurate it is the better. And then I share that model with my receiver. And I say every time I'm now getting a new measurement, I'm going to I read a real value, and also use my predictor model to predict that value. If they are close to each other, close within a range of a threshold, I'm not going to send the value, because I'm assuming you have the model and you can go and generate the same value, right? Let's say you're expecting me to tell you the temperature, what is the temperature here, but both of us, we have the same model. We can also run a prediction. We give the time and we get what the value is. I read the real measurement and also run the measurement via my predictor model. And I look at the difference is smaller than 0.2 degree. And if it's smaller than 0.2 that degree, I don't send the value to you. And if I didn't send it, you know your predictor has given you a reasonably good value and you can use that. And if suddenly the change was much higher than 0.2, I will send the value. Then we have an agreement between the source and destination. Both of us, they will run the model, and if we didn't receive the value, that means the value was within an acceptable range, within a threshold of range. And if it was bigger, means you need to send the data. By doing that, you're saving a lot of not sending lots of measurements. Like we said, sending data and communicating has more energy footprint. That seems an interesting model, but has some flaws in it, or has some issues, not really flaws, but some issues. Can you think of what could be the problem? I'll tell the easy one. If your environment is very unpredictable, you will generate lots of predictor won't work very well. And then you need to continuously do the calculation and see what is higher than range and send it. This will work well in the areas which the value is more predictable. Obviously, predictability here, we are taking advantage of predictability. What else could be the problem? Any idea? Let's say my sensor does the measurement, you're expecting your application to read the value. If you didn't read the value, what do you assume? Your predictor gives you the right measurement, right? Because you didn't hear from me, and you're assuming the predictor gives you the real value. What happened if the network was broke down, or if the node was actually broken? What can you do to resolve that issue? These are the type of questions I'm going to ask in the exam. I'm expecting design ideas. To hear what do you think of designing a system. What would you do to prevent something like that? Actually, that was an exam question at some point.
Send a message every now and then.
Send a message every now and then. When would be that now and then?
So you can make it the same interval.
You make it the same interval, yes?
Yeah, and then so either send the data or send the output.
Instead of sending data, you might send just a bit to say, just live, I'm here. And if you didn't get that, you're assuming the node is also not functioning. Yeah, something like that. Okay. And obviously the main target was interpretation of data. Here we mainly today focused on actually doing some analytical models, some calculations, taking the raw observations, creating patterns, looking at the changes, looking at the models. But eventually you want to train models to be able to interpret that data. I think in a couple of weeks we look at some examples of applications. But as I said, here we are not going to get into very much into the machine learning, training data, or time series data analysis. Maybe if we had another advanced Internet of Things course, we start looking into those as well. I don't think we have a time for this, but if you're interested in, do the calculation, send your results to me, and I'll check and tell you if you have done the correct calculation. The idea is we have 10 values here, and I want you to calculate the PAA based on 3, means your frame size will be 3. Once you have done it, you take 3, divided by 3, well, here will be the same, and each 3 of them will become a PAA, and take an alphabet of Sachs alphabet of 3, and write what will be the alphabet. Before we finish today, what do you think would be the big problem in Sachs in applying to IoT? By the way, Sachs was not designed originally for IoT. It came from financial market and time series data analysis, but can be used for IoT data. What would be the big problem if you want to apply Sachs to your IoT data. Let's say if you want to implement SACs on your X1000 for your second assignment. Your second assignment is aggregation, and we don't want it. That's not a compulsory part of it. We have asked for simple ones, but if you want to add an advanced feature, it could be SACs. Power consumption. In terms of calculation, I think the footprint of that calculation is not that high, because especially if you hard code all your alphabet size, all the tables, everything, what you need probably is a standard deviation and a mean calculation. Higher than mean and let's say maximum minimum calculation, but it's not that complex. What did any other issue comes to your mind?
Turning it back to actual data.
Sorry?
Turning it back to the number.
Turning back to the number. Depends if you want to. If you want to reconstruct your original data once you created SACs, go back to the original one. Depending on the PAA, assumption you made on PAA to aggregate it will be difficult. But the rest you should be able to actually reconstruct. Any other?
Storage issue.
Storage being an issue. You're getting closer to what I think will be a problem. We might find out a problem. In what sense do you think storage will be an issue?
It's a very large amount of data.
Yeah, you're getting closer to what I have in my mind, I think would be a problem. Any ideas, any suggestions? We need mean and standard deviation. Right? To do mean and standard deviation, you need a finite number of samples. If you're continuously measuring something, what is that finite? When will you stop to calculate your standard deviation? When will you stop calculating mean? Probably that got to be large enough to have that Gaussian distribution, to have all the variations in your data. If you're measuring like, I don't know, temperature, you probably have large enough to cover the daytime, nighttime. I don't know, if you're looking at the seasonal, you could have large amounts of data. You have all the seasons, all the averages, I don't know, depending on your application, you need to have a large number of samples to be able to create that. But if it's too large, first it will take too long to collect that data, and storage will be an issue. If it's too small, probably it's not a good representative. And then if you're continuously measuring it, at some point also you might decide to retrain your model, to change the values again. There are different ways of looking at it. The SACs is, as original one, is mainly designed for offline data. You have offline data, you have all your data, you can measure it, calculate the standard deviation, you can calculate your mean, take your normalized ones. If you do it with online data, you need to decide what portion of data you're taking to calculate your mean and standard deviation, but that won't also stop you to have a policy of updating those values once in a while. I'll leave it to you to decide how you want to do that, but if anyone is interested to discuss it further, you can come and see me, drop me an email, or anyway, or you can come and talk to me during the lab hours. Any other questions? I think I've finished my idea. See you in 10 minutes in the lab. Thank you very much.